All right, welcome everybody to week 10, day 1. The make sure you submit all of your pictures and stuff onto Canvas. The Canvas wasn't live until about half an hour ago, so I have extended the deadline on the assignment till midnight. So we'll talk about the solution to it later, I guess. All right, so let's talk a little bit more about graph theory. We're not quite done yet. We've gone over shortest paths. We've gone over minimal spanning tree. Today we're going to talk about max flow, which sounds like something a rapper would do, you know. Maximize your flow. Let's see here. Okay. Yeah. All right. So we're on to part 3 of graph theory. And you'll have one more graph theory programming assignment today. There's a couple we could do. We could do another Dijkstra's, do like maze solving and things like that. But I think we'll do Markov chains instead. Now I'm only going to lecture for an hour. There is an issue with the Zoom link for the Laden talk, so that whole thing might get scrubbed. I don't know. So whether or not we actually get to do the X credit is kind of up in the air right now. Yeah, it's going to require a password, and I don't see a password. So Dune. Oh, interesting. This Thursday the 14th, we're hosting a webinar with the 2 sound designers from Dune. That's pretty cool. All right. So this is coming up in 2 days. All right. Cool. So that could be fun too. All right. Can we go over the quiz? Yes, absolutely. Why don't we do that first? All right. So again, the quizzes are there to see if you know what you're talking about and to see if I know that you know what you're talking about, specifically if you're learning the material or not. Let's go over the quiz statistics. Oof, not good. All right, so we'll have to go over minimal spanning trees again. All right, so did you guys see the explanation of total cost? Like when you launched it, it tells you what total cost is, right? So if you have a graph here, the minimal spanning tree would be the 1, the 2, and the 4, so the total cost is 7, right? The 1, the 2, and the 4. So with the quiz, I guess we'll have to do another minimal spanning tree one. So the minimal spanning tree of this graph is what? So there's a couple different ways you can do this. You can use prims, you can use crystals. If you use prims, you pick a graph. Let's just toss this into OneNote so you can follow what I'm doing. Do you guys like the Rick and Morty and Akihabara thing? Akihabara is come on, OneNote. Aren't you launching? There we go. It is a place in Japan that is famous for selling random electronic parts. It's called Electric City sometimes. And when I went there in 2009, it was still, I don't know. I think Rick and Morty might have been exaggerating a little bit about how much it's changed, but yeah, you could just go there and you can just buy, just like there's just a little stall like that screw seller's stall, and one stall I saw was just power cables. Like you just go there and just buy a power cable, and they had every kind of power cable you could possibly ever need, and it was just a really cool place for nerds, electronics nerds, but also there was a store I went into that was just all model trains. And so, you know, if you're a model train nerd, you'd go in there and purchase them, a little working model train and stuff like that. It's a cool place. Okay, so let's see if paste you. Really? Okay, there we go. All right, let's zoom you out. Yeah. You can buy transistors by the scoop, you know, they just weigh it out. They just charge you by weight. It's like going to a grocery store and buying granola, you know. Okay, so you guys want to do prims or crystals? Yes, you want to do both. Okay, fair enough. All right, so prims, give me, you can just pick any node. Somebody give me a letter from A through H. Give me a letter to start on. B, all right. All right, it's on the left-hand side. Okay, so what is the edge with the smallest weight that is not attached to our graph, our processed graph? Which edge has the smallest weight that is not currently attached to our graph? Coming out of B, coming out of our graph. For prims, you start at a thing and you always look at the list of edges. So our two options are 2 and 6. Okay? So we add 2 over here, and now this is our graph. Now we've got 3 options: 6, 3, and 1. Which one's the smallest? The 1. Okay. So this one's part of our graph now too. Now we've got 6, 3, 6, 1, 5, and 9. Which one is the smallest? 1. Okay. Okay. I should be writing these down now too. Which one? 2, 1, 1. Okay. Now we've got 6, 3, 6, 10, 7, 5, and 9. Which one's smallest? The entire class can't type for some reason. Maybe they're just AFK. In the help center. In the help center? You know, chat permissions. Interesting. Only the tutors can type. Oh, that's, no wonder. Okay. Unlock. Oh, yeah, the chat bot didn't. You see that? I typed unlock down, and the chat bot didn't respond. Okay, yeah, sorry about that. I don't know. The bot must have barfed. Okay. Well, okay, so all of you all that were just sitting there AFK and idling and not participating, now's your chance. Out of all of these nodes here, out of all these edges here, rather, which one is smallest? Six, 3, 6, 10, 7, 5, 9. Yes. 3 is the smallest. Okay. Now, of the ones we got left, we got 7, 5, and 9. Which one's smallest? Very good. A lot of times it helps to just do this on pen and paper, you know. And then of the remaining ones, which one's smallest? 3. So let's see, what do we have here? 3, 5, 3. And then what's the last one? 4. And we can either do this one or this one, it doesn't matter. They're both minimal spanning trees. Okay, so the total cost is 2, 3, 4, 5, 6, 7, 12, 15, 19. Now let's see if I did it right, because I did this in my head. Damn it! I did it wrong. I thought I had changed that to 19 too. Okay, so I literally typed in 19. That is so weird. The first time I didn't hit update. Yeah, I went back and I edited it and changed it to 19, and then I didn't change update score. Okay. Damn. It's unfortunate. Well, 3 points for everybody, I guess. Alright, so let's do this one. Yep, 3 point for everyone. You're the worst that got 15. You get a free point too. So there you go. You got an extra point for guessing the wrong number. All right. Yeah, in Canvas you edit it, and even if you hit save, it doesn't save the change unless you click on the thing, update, then save. It's super frustrating. All right. Okay, so let's do crystals for this one. So for crystals, we look at the smallest edge anywhere on the graph. We don't start with one particular one like we did for prims. For prims, we just picked one to begin with. So for crystals, we just pick the smallest edge anywhere on the map, which is a 2 here. Okay. So these two fellows here are part of the processed graph. All right. Now, what is the smallest edge anywhere on the map? So, yeah, 3. For crystals, you can grow a forest of trees. Okay. Yeah, A and C and E and F. So there's another 3 on here, so we can add this one in here. Okay. What's next? 4? Yeah, okay. And here. And then what's next? 5. Now this 5 already connects 2 people that are in the same set. This connects 2 people in the same set. This one, however, is not in the same set. So our total cost here is 7, 9, 14, 17, 21. Let's see if I screw that one up too. 21, good. All right. Make sense? I'll do a couple more of these on the quiz today. All right. How's that work out for you guys? Okay. You want to do more? Nope. Okay. All right. So let's talk max flow. All right. So max flow is another graph algorithm. Let's see. So in this case, it's a directed graph. And what you're trying to do is try to see, in this case, we're trying to see how much data or how many cars. Let's see, max flow can represent a lot of different things, right? Let's say that these edges here represent roads. Like this is like the I-5, this is the I-15. You know I'm from Southern California because they call it the I-15, the I-5. This is the 41, the 99, you know, whatever. Okay, and so maybe it can support 3 trucks per hour or something. I don't know. Okay. This is our start. This is our finish, sometimes called the sink. Okay. And we're trying to see how many trucks can get from A to G per hour or whatever. And these numbers indicate trucks per hour. And so, how do you do it? But do you understand the problem, right? Because like, you know, if I send 3 trucks an hour this way, and then 3 trucks an hour have to come out one way or the other. You know, maybe sending 3 that way, and then there's room for 3 trucks left there. This one's going to be at saturation. This one's going to be at 3 out of 9. And if I send 3 trucks an hour this way, then 3 trucks an hour would come up this way. And maybe we'll send 1 truck an hour up this way, and 2 trucks an hour this way, and then we'll send that truck that came up here this way, and the 2 trucks this way, we can send 1 this way, 1 this way. I don't know. Okay. So, that makes sense. You're trying to see what's the maximum number of trucks you can push into the network from A through G. Or it could be routers on the internet. And these numbers here indicate gigabits a second or something. And you want to see what is the max flow from A through G. So if you have a router that can transmit at 3 gigabits a second this way, and this router can send 2 gigabits a second that way and 6 this way. If you're trying to send data from A through G, what's the maximum amount of data that you can push through the system? You guys understand? There's a lot of silence on the chat channel right now. Your brain is loading? Okay. No. Let's go over some applications for it. Wow, that font's really hard to read, isn't it? Let's switch that font out. Design. It's a lot of text on one screen. So yeah, bandwidth going through a network. Traffic planning, for example, if you're thinking about building a new road, you guys know how the 99's like this and the 41's kind of like this, and then there's like Avenue 12 and Avenue 18 and 21. You guys know what I'm talking about, like up in Merced area? You guys know the roads up there? 41, 99. 12, stuff like that. So a lot of times people want to come down the 99 and then kind of hook over and then come down the 41, right? And these roads, these horizontal roads kind of suck. Like, okay, so anyhow, 99's a freeway or a highway or whatever. 41's another one. And they're, I guess, okay fast. Like, they're not super fast, but they're faster than driving surface streets. And then one of the big troubles with the road network in the Fresno area is that there's really no east-west interstate. There's 180, which is like way down here somewhere. Like the 180 runs across like that, and the 168 kind of goes like that. So if you want to go from like San Francisco, like San Francisco's over here, and you're trying to go to like Clovis, then you have to like come down the 99. You either have to go down way south and then take the 180 over and then go north again and then hook over here, or at some point you're going to have to take one of these like lateral roads, which are, one lane in each direction. And so if you get stuck behind a truck, you're stuck behind a truck, and there's not a whole lot you can do with it. So you can think of this in terms of a max flow problem, right? You've got your source out here in San Francisco, you got your sink over here in Clovis, and you're trying to see how much traffic you can push through the system. Avenue 9 is faster, yeah. So there's a bunch of these kind of like horizontal lines like this, and I guess the accepted solution is to take Herndon a lot of times, because Herndon's kind of designed as an expressway. Even still, it's got traffic lights on and stuff like that. So, so if you're doing traffic planning and you want to figure out like how is putting in a new road going to affect traffic flow, you use a max flow algorithm. You might put in a hypothetical road up here or a hypothetical interstate down here or over here, and then you see how is it going to affect traffic flows in the area, because you have a certain number of people coming in from the Bay Area, you have a certain number of people coming in from LA, and you model this, and computer modeling is like a really big thing. Like I worked doing modeling for years. I was a tuxedo model in high school, but that's not what we're talking about. So we modeled different physical things. And if you work in climatology, you're going to be doing a lot of climate models. Like climate science is basically modeling, right? And in this case, traffic modeling, right? So if you work for Caltrans or something like that, and you're involved in planning out new roads, you're going to run Yeah, Zoolander, exactly. You're going to run lots of models and simulations trying to figure out how is this going to affect it. Or what happens if we close down the 180? We got to do construction. What happens if we shut down the 180? How is the traffic going to reroute around it? Right? Think about it. If you close down the 180, then all the traffic that normally goes on the 180 is going to reroute around Herndon, or it might come up to the 168 and come down that way, or they might just take surface streets up here. You know what I mean? And so when you have a graph showing all of your roads, if you cut one of the roads, like let's say we cut the 180, then the max flow is going to have to route around it. So this is a useful algorithm. It's different from Dijkstra's. It's different from minimal spanning tree. Okay, minimal spanning tree and Dijkstra's is pretty similar, right? Like a lot of students write max or minimal spanning trees by accident when they're trying to do the Dijkstra's algorithm. Okay, so this one's different. All right, shipping. That's topical. Right now, our global shipping networks are all screwed up. The pandemic has caused widespread disruption in the international shipping lanes. Couple causes for that. The quarantine has slowed down the amount of cargo that can come in because they're doing like a lot of testing and things like that to make sure that the cargo doesn't spread. People that are on the ships have to get vaccinated, and the countries don't coordinate vaccinations between them. And some sailors have been vaccinated 6 times because each country doesn't recognize the other country's vaccines. And they've been stuck on the boats for 18 months because they don't allow sailors to come ashore. And so people are starting to just quit. And like Long Beach is all backed up. There's container ships for miles off the shore of California right now. And it's just this giant mess. And this kind of thing can be modeled using max flow. Okay? What's the maximum amount of cargo we can push from Shanghai to Long Beach, right? Or from China to America, more generally. And if we do this to the system, how is that going to impact shipping? And my guess is probably nobody did that, right? They just simply said, all boxes have to be inspected, and that's going to slow everything down. Assigning tasks to employees is also a use of max flow. So if you've got 5 different employees and they pass work to each other, right? So like if I hand off my paperwork to somebody, and then that person hands work to somebody, and that person processes and hands work to somebody, that can be modeled as max flow as well. So where do you hire new people to speed up the total throughput of your company, right? So a lot of very interesting things involving planning and things like that usually. Ooh, that's cool. Is the Evergiven still here? That probably didn't help. Huh? When that blocked up, everybody started going around Cape of Good Hope. There's still people going around Cape Horn. That's cool. Valpo. There it is. Yeah. The Valpo is still pretty busy. All the way up to Stockton, huh? Interesting. Yeah, in theory, you used to be able to take a boat from Fresno all the way down out to the bay, but these rivers don't flow anymore. More like Firebaugh, I think. Slow, Santa Barbara. Hey, how you doing, Long Beach? That's pretty impressive. So, how long have they been stuck in port for? Just going around in a circle. Okay, yeah, that's pretty cool. Still feeling the effects of the Suez Canal. Yeah, the Suez Canal, the pandemic, and like I ordered a couch back in like April or May or something like that. It took like 5 months for it to come in. Yeah. Bicycles, you know, all that kind of stuff. It's all super screwed up. Okay, so here we go. Ford Folkerson is one of the max flow algorithms, and it works like this. Given a starting point and ending point, what's the max flow between them? Okay, and there's two different ones. There's Ford Folkerson and there's Edmonton Carp. And Ford Folkerson is interesting because the running time is proportional to the max flow, which is weird. Because you would think that like whether the max flow is 10 or 100 or 1,000 doesn't matter, but Ford Folkerson is actually proportional to the flow of the max flow of the graph, which is really strange. Edmonton Carp runs in order v squared e, which means the square of the vertices times the number of edges, which may or may not be faster than the flow of the graph times the number of edges. So depending on which one it is, it's going to be faster. Okay. So what you're going to do is you're going to push flow through the route, and when you push flow through the route, you like if you have a pipe that holds 5 gallons of water per second going through it, and let's say you push 3 gallons of water per second through it, it's got 2 gallons per second remaining, right? Does that make sense? If you've got a pipe that can handle 5 gallons per second, you're currently putting 3 gallons per second through it, you got capacity of 2 left. Does that make sense? So you just keep pushing water through different routes through the system, and each time you push water through, you mark down the remaining capacity. Does that make sense? And you keep doing that until there's no capacity left. You see it? All right, max flow, yeah, wrapping. Okay, so here we go. So how we do this, I'll explain in a bit. But you see how we're like, imagine these are pipes, and so this pipe here can hold 3 gallons per second. This pipe can hold 2 gallons per second. Whatever. And this one can hold 1. Okay. So do you see how this works? So now that this one is at capacity, it's essentially detached from the graph, right? Like you can actually just be like, all right, there's no pipe there anymore, right? So we've pushed one through the system, we've detached this one. There's like dead silence on the chat channel. Do you guys do you get the concept here? Okay. So why would we start with this? Well, what if we ran the shortest paths algorithm? Yeah, since E through G is at max cap, it's essentially like there's no pipe there anymore. Like you might as well just take out an eraser and erase this pipe. E and G are not connected anymore, so you don't even have to consider it in future calculations. But how did we get this? Well, what if we ran Dijkstra's? What if we ran Dijkstra's and we got the shortest path from A through G? That would give us this path right here, right? Because every other path is going to be longer. 3, 4, 1, you know what I mean? So this is the shortest path between these two. And then once you find the shortest path, then you figure out what the max flow of that path is. Do you see how the max flow of this path is 1? Why? Why is the max flow of this path 1? Vargas? The last one, yeah. So the max flow of this whole path is whichever pipe is the smallest. You can have a big old like sewer line and a smaller line and a smaller line. Whatever the smallest line is going to constrain how much flow can flow along that path, right? Yeah. So let's do the next one. Let's run Dijkstra's again. Okay. Shortest path is again this way, right? Because there's no other way this way. So the only way in to G is going to be this way, right? And the fastest route between A and D is here. There's 2 this way. And this is 3, 4, and 1. Okay. So why is the max flow, Shahab, why is the max flow from A to D to F to G 2 now? Why is it sending 2 gallons per second through these pipes? Because we've already used up one of the capacity here, right? So there's 2 left. So we then are going to max out this pipe. And so now we can essentially just like, you don't exist anymore. You don't exist anymore. All right, shortest passes again. Exactly. Yeah, very good. So Corrente, what is the shortest path from A to G right now? What is the shortest path? Anyone else? What is the shortest path from A to G? There's only one possibility. A, B, C, D, F, G. Yeah, because E to G's gone, A to D's gone. So there you go. So I think the X credit talk is only available to Fresno State students. So sorry, we're not going to be able to do it. Let's delete you out. Okay, so Cheryl, what is the max flow from A, B, C, D, F, G that's remaining here? What is the maximum amount of gallons we can pump through the system? From A to B to C to D to F to G. Got 3 gallons per second this way, 4 gallons per second this way, 1 gallon per second this way, 4, and 7. So what is the smallest value along that route? What is the smallest pipe? Because that's going to constrain the whole thing. You can have a big honking old pipe over here. This could hold 9,000. It doesn't matter. Nope, 1. This pipe here from C to D can hold 1 gallon per second. So it doesn't matter that you can have 9,000 gallons per second this way. This entire link this way is constrained to just 1 gallon per second. Okay, so we send 1 gallon per second this way, this way, this way, this way, this way. And so now this is cut off, this is cut off, this is cut off. We're done. Except, is there one other way? Let's see here. Yeah, I think we can steal a gallon per second this way. Yeah. Mm-hmm. Yeah. So then we're going to steal one flow that way, and we're done. Okay. And so that's max flow. So what we have here is a situation where we could reroute. We had gallons coming this way, but we could send that gallon this way instead. Okay, so that is the algorithm. Okay, and so what you'll notice is that as we send flow down a pipe, we're essentially cutting it, right? And so some people call max flow the same thing as min cut. Imagine that these are bridges. Imagine that they're bridges. And the bridges represent road capacity, right? So you've got, LA to San Diego or whatever. And there's 3 bridges connecting in parallel, let's say. Or the bridges can hold 3 trucks per second or whatever. If you want to detach, LA from, like, let's say San Francisco, and you're like a military, and you want to come in and blow up bridges, okay? How many bombs do you need to drop? Each bomb costs, one bridge, 1 bomb, let's say. So how many bombs do you need to drop to detach LA from San Francisco? Okay. So that is called min cut. So it is the minimum amount of bombs needed to cut A and G off from each other. So you're going to drop 1 bomb there, take out that bridge, drop 6 bombs? Nah. Drop 1 bomb here, cut that one, and 3 bombs here. So a total of 3, 4, 5 bombs, and you can cut this whole traffic network in half. Okay? And now nobody is going to be able to transport anything from LA to San Francisco with just 5 bombs. Does that mean free extra credit? No, it wasn't extra credit for you guys anyway. So, I just deleted it. You guys understand? So max flow is the same thing as min cut. Right, because with these 3 bridges out, this bridge out, and this bridge out, there's no way that we can send anything from LA to San Francisco. Yeah? It's just so much silence on Discord today. It's a different paradigm, right? Like, this is why, like, when students ask, like, what does a vertice represent? What does a edge represent? Well, graph theory is so flexible. Like, there are these algorithms, and they just work on edges and nodes, vertices and lines, whatever. So, these, in general, there's these set of generic algorithms, and they can be, used for targeting bombs on, a country's bridge network. It could be used for trying to lay out pipes in a house to try and figure out, what pipe layout is going to give you the best flow from the place where the water comes out to your sink or whatever. So all of these things are very big and broad and flexible, but they do different things. Like, do you see how this is a different way of thinking about a graph than Dijkstra's? Dijkstra's, these numbers would be distance, right? This number would be distance, 1 mile apart. With max flow, it's like a gallon per second, or it's a gigabit a second, or it's a truck per second. It's flow through a network instead of a distance. So you just kind of have to wrap your mind around it. And minimal spanning tree is, it's pretty similar to Dijkstra's, except rather than trying to minimize leaving LA and going to San Francisco, you're saying, if these are all the cities in California, how can I connect them with as little cost as possible, let's say. Okay. So those are the three big graph algorithms that we go over in this class. Shortest paths, minimal spanning tree, and max flow. Okay. So A star is a variation of Dijkstra's. Dijkstra's is basically breadth first search, right? So Dijkstra's, if you're trying to navigate from San Francisco to LA, if you do Dijkstra's, which you're doing for your homework assignment right now, which again I've moved the deadline back to midnight, so if you need a little bit more time to get it done, let me know. Dijkstra's will search to the north as quickly as it searches to the south, right? Which isn't especially efficient. You know what I mean? Like if you have San Francisco up here somewhere, and you search everybody 1 away and 2 away and 3 away and 4 away, I mean, sure, it'll eventually find a route to San Diego down here, but it's going to be searching to Oregon as quickly as it's searching down to San Francisco. So A star is a variant of Dijkstra's that prioritizes searching towards the target over searching away from the target. If that makes sense. You're still having a tough time with it? Well, why don't we take a break, and then when we come back, we can talk about the Dijkstra's assignment and maybe see if we can figure out what's going on here. So do you see though how this isn't searching like in concentric circles? It's kind of like searching towards the target, right? Rather than just going out and backwards and stuff like that. So A star will add a cost to moving away, is essentially how it works. A star is like one line different from Dijkstra's, basically. What you do for A star, it's Dijkstra's algorithm. I'll just summarize A star in just one line. It's Dijkstra's, Dijkstra. It's Dijkstra's, but the cost in Dijkstra's, the cost is the total distance from start, right? You guys nothing on this? Like when it goes into the priority queue is sorted on the total distance from start, right? Yeah. Like you're adding all these tiles to the priority queue, and they're sorted based on total distance from start. A star is the exact same thing. A star is the exact same thing, except you add in distance from the end. So what you do is, if you want to see how far away this person is, you're going to have some computed distance from the start, and then you just do a little bit of Pythagorean theorem here. Distance from end, like as the crow flies. Okay. So the cost of this fellow over here, he might be the same distance away from start, right? He might be the same distance away from start. Start's down here. Like as we're taking these paths, this guy might be a distance of like 100 tiles away. This one might be 100 tiles away. They might be both 100 tiles away. But with A star, this one is going to have a lower cost, a lower value in the priority queue. Why? Because his distance from the end is smaller than this one. So what A star does is it prioritizes tiles that are closer to the end zone. And what that does is it has a tendency of finding a route more quickly. Like you'll hit the end more quickly because if you're in San Francisco, sure the fastest route might be through Washington, D.C. Like in theory in Dijkstra's anything can happen. There might be a route through Washington D.C. that's faster somehow. to San Diego. But in general, we want to check the routes coming southbound out of San Francisco, right? And we want to check the routes southbound out of LA. If we're, you know what I mean? Like, it just kind of makes sense, right? Like, in general, like, and there could be a trap, you know, in a maze, there's no guarantee that, you know, like, there could just be a wall like this, you know, that goes all the way except to the very last square here. And maybe the shortest route would have to come around this way or something. But if, you know, if it's not degenerate like that, in general, A star will find a route much, much faster. Because it prioritizes tiles that are closer to the target rather than checking in concentric circles. Does that make sense? So it's one difference. It's Dijkstra's. Again, Dijkstra's. You make a priority queue, right? And the priority queue is just based on the distance from start. And then all A star does, A star just adds in plus distance to the end as the crow flies, because you don't actually know the actual distance. It's a guess. That's why it's called A star. The star means it's a heuristic. It could be wrong. You know, it's not, you know, the going to LA might not necessarily be the fastest route to San Diego. In fact, a lot of times going around LA is faster, you know. But it's like, we'll check the route from San Francisco to LA to San Diego prior to checking, you know, San Francisco to San Bernardino to, yeah, you exactly. All it's this much code different. All you do is you add the distance for a tile is you add in the Pythagorean theorem, right? You take this guy's x1, x2, or x. Sorry. Give me a fresh sheet of paper here. Right, you guys all know the Pythagorean theorem, right? So you just add that into the Dijkstra's thing. My location is x1, y1. The ending point's location is x2, y2. That's it. That much different. Yeah. And so it tends, like, especially when, you know, you have like a non-degenerate situation. Like, mazes can be degenerate, right? You can have maybe a straight line all the way to the end, except there's a wall at the very end. And you got to back up and, you know, try other routes. But in most, you know, real life situations, if you're programming a robot to like navigate around inside of a classroom or something, the first route you'd want to check to see if it's fastest is just, what if I just drove right at the target? You know, like, let's just try that one and see if that, you know, let's see if that one's fastest. You know, and so A star will do that for you. Okay. So let's go ahead and take a break, 15-minute break, and we'll come back at 11:15. And I'm going to have a lot of students messaging me right now saying they can't get into the lecture because it's only open to Fresno State students. So I'll be dealing with that. All right, see you guys in a bit. All right, let's get going again. And I don't know what's happening to all the students in this class. Cohen's here, Shab's here. You're on your way back? All right. So let's go over the Dijkstra's assignment. So who was having issues with their code? Let's see if we can go through and see if we can figure out what went wrong. Vargas, okay. Vargas. CD bridges, mountains. I'm probably going to reveal your API key, so sorry. All right. Whew, look at this. All right. Okay, let's, I guess, take this from the top. So you got the bridges.h included, tile.h, color grid, including std, including bridges, path is -1, water is -2. All right. Got some functions here. Got your main. You got your API key. Might want to change that after the assignment's over, or after this lecture's over, or now. You know, either way. Create the bridges object. Cool. Set these guys to 0. Cool. Opening up test.dat, or you can pass it in from the command line. Made a 2D vector. Cool. So read data, width, height, max val, min val, and file name. You change these to be call by reference, I'm sure. And pulled out the call by pointer stuff here. Changes to man paths, Dijkstra's. Good. Okay. So you're going to enter the starting row and column, ending row and column. All right. And then I'm going to call find path, which looks exactly like the old find path Vargas. I'm not sure. I'm not sure what you accomplished with this one. I'll delete that one. And then you're getting a pointer, the color red, and you're passing that to bridges, and it's visualizing it. All right. And you don't need that anymore. And so there we go. Okay. Hey, your main looks fine to me. So let's go ahead and take a look at read data. Have you verified that read data works, Vargas? Like you've made a little sample map, printed it out, tested it. Okay. Again, one of the points of this assignment was to teach you all how to test your own code. Because in real life, people aren't going to give you, you know, test cases and things like that. I mean, I guess sometimes they will. But, you know, you need to learn how to write tests for your own code. And so making your own map and feeding it in and seeing if your code works and all that stuff is a big part of the process. So here, okay, so we're going to read the width and the height from the file. Make a 2D vector based on that. Max val, min val. Did we talk about moving? How like when you return a vector, it moves out of it rather than copying out of it? Did we talk about that? I talked about it in 40. Did we talk about that in 26? This part here. How moving works in C++. Don't think so? Okay, I'll talk about that in a second. Okay, so we're going to start off with max val is int min and min val is int max. Good. Alright, so reading in from the file, a bunch of things, and good. So, Vargas, you discovered that water sucks, right? Is that a determination you made? So if you read in a negative number, then you set it to -2. Right, and so a lot of students are crashing, and again, this goes back to what I was saying about, you know, testing your code. In this case, the crash actually wasn't your fault. The bridges code crashes if you pass in a negative elevation to it, because the bridges code assumes that the lowest elevation is 0, but the lowest elevations actually can be negative on the California map or in the Tahoe map and things like that. So their code that did the colors here would give you a negative color, and that would segfault. Excuse me. So it's actually not your fault that it crashes. It's a bug in their code. But how do you identify that? How do you track it down? How do you figure out what's causing the problems? That's all skills you need to learn as a computer science major. So here we've got Vargas' solution, which is just to mark it as water, and then down here he's probably going to have, yeah, right. You probably should say water for that, Vargas. I mean, you went to the effort of making these things, right? So probably should change this to water. Just, I mean, yeah, that's why you made them, right? Okay. When I wasn't handling negative values, it was only core dumping part of the time. Yeah, not all the maps have negative values on it. So Colorado would work fine. Yeah. This is a pretty deep issue in computer science, which is that your with Korea, yeah, it should core dump. It's undefined behavior technically, but the assumptions that you make are the lethal thing in computer science, right? What assumptions you make really can cause you pain and suffering, right? Is it reasonable to assume that 0 is the lowest elevation there is? It is for height, for people, right? People's heights can't be negative. Can elevation be negative? Yes, it can be, right? And so somebody probably is like, all right, 0 is the smallest, and you just, whatever assumption you bring in there, if it's not good, you're gonna get issues, And so one of the things that I always try to hammer home in my 40 class is like what Vargas did here is good, right? So he set the maximum value to be a negative integer and the min value to integer maximum. This code won't work if there's 0 points in the array. He's got it. No, he does handle it. Perfect. Yeah, so it's perfect. And then as he goes along, if you ever find somebody who is bigger than the max val is that value. If you ever find somebody that's smaller than the min val is that value. And so this code here works great. And if you wanted to do this with like doubles or something, there's numeric limits in C++ that hold max doubles and all that kind of stuff. Yeah, so all this looks pretty good to me. Let's get down here into get image. So you're grabbing the data, converting it to a float. And if it's -1, you make it red, I guess. If it's water, you make it a watercolor. Otherwise, you're making it gray, so you're not colorizing the map. That's fine. Pixel value, which is a value from that probably should handle min val as well. Right, so if all of your elevations are from like 1,000 to 2,000, then what this code here is going to do is have 1,000 be marked as 50%, right? Because max val is 2,000. So the pixel value is 1,000. It's gonna draw everything as like the minimum color is going to be 50% gray, not 0. And so you need to add in. You need to do lerping. Is what you need to do. So Vargas, do you know lerping? Do you know how to lerp? So you need to lerp from. Okay, so lerping is a really important thing in computer science. It stands for linear interpolation. Linear interpolation. And that, basically, in algebra. So if you've got the minimum elevation is 1,000 meters and the maximum elevation is 2,000 meters, the input is going to be an elevation. And then the output should be a value from black to white, right? And right now what's happening is that if you pass in an elevation of 1,000 meters, it's doing 50% gray instead of 0. So you've probably seen this kind of stuff before in algebra. The good news is they've actually added lerping, lerp into C++ 20, I think. They finally added a function for that. It's very common. It's a very common thing we do. We do it all the time in video games. We lerp all the time in video games. You can think of it as like on a car, when you've got your climate control on the car. If you turn it all the way down, that's 60 degrees. And if you turn it all the way up, that's 90 degrees. And so that's a linear interpolation. As you move the slider from 60 to 90, you put it at 50%. 50% is halfway between 60 and 90. 60 plus 90 is 150, divided by 2 is 75. So if you have it 50% between 60 and 90, it'll be at 75 degrees. And so as you move that slider up and down, that slider up and down is called alpha. 0, 60 degrees. 1, 90 degrees. And so you have 60 degrees, 90 degrees, and then 0 to 1, essentially. And then that gives you a, so you feed in like 0.75. That means the temperature slider is 75% of the way to 90. And what would that be? It'll be like 83 degrees, something like that. If you have it like 75% of the way up. So there's this function lerp. And so you can pass in the minimum elevation, the maximum elevation, and, you pass in black, white, and then this is the percentage it is from minimum elevation to maximum elevation. But this was only added in C++ 20, I believe. C++ 20. There it is. Okay. So yeah, that's how you should be doing that. You should lerp that. That's not what we're here for. What we're here for is Dijkstra's. So here we got find path, taking in the elevation data. You don't need image width. You don't need image height. Those can be neglected. Starting row, starting column, end row, end column. You do need. Okay, so you got a hash table of all of the tiles you've processed. You've got a priority queue of all of the tiles to come down the line. That's all correct. And then you start with the starting row, the starting column. So you start with one tile in the to-do list. And its parents are set to -1, -1. That means I'm the start. And so when you backtrack to get your solution, that tells you when you're done. Okay. Some people would set their parent to be themselves in that case. Okay. All right. So elevation data at start x start y equals -1. So you're marking the you're changing the map and setting the elevation to be -1. I might cause a problem. Because what if you need this elevation later? What if you need to, I don't know, see what the difference in elevation is from your current tile to another tile? Yeah, it's gonna mess up your distance calculation. Okay, tile shortest, I don't know what that's all about. Tile center. Okay, so 10 times. You're only doing this 10 times? Oh, I see. You're capping it so it doesn't run forever. Okay. Smart. Smart move there. Okay. So this is exactly what you should do. So your standard graph traversal algorithm is this. You've got some to-do list of tiles or whatever vertices that you're going to be processing. You would pick one off the front of the list. In this case, it's sorted by minimal distance. That's the tile comp thing there. It sorts it by minimal distance. And we top it and pop it. Top gives you the tile. Pop deletes the tile off the front of the queue. You have to do both. I personally think that pop should return the tile and delete it at the same time, but it's just me. So if not is in, we add it to processed. I would probably go a little bit further than that. I would say if is in processed center. So I'd say if the tile has been processed already, continue. Because I don't want to do the rest of this. If I've already processed this tile, just no. Just stop. Because what's going to happen is that if you've already processed that tile, sure, it's not going to add it to the process queue, but it's going to just keep going. And it's going to push all its kids again. So you're going to fall into an infinite loop. Okay. If we have seen this tile before, then skip. Might not be an issue because you might have other checks down here that stop it from falling into an infinite loop, but this is always a good idea. Whenever you get something out of the to-do list, just immediately check to see if you've handled it already. And if you have, just throw it away. Just continue. Continue on with your life. Okay, so if center.x minus 1 is greater than 0. So center is us. Okay. So if we are greater than or equal to 0. Okay, so you're checking to make sure that we are not against the left edge of the map. Okay. Okay, so we make a new tile that holds x, y, x minus 1, so it's the person to our left. It's not top, this is left. So it's going to hold the person to our left, x and y, the parent is us. The distance they are is the distance to our current tile plus find distance from, find distance at, let's put that. Find distance from their xy L of data at, yeah, this isn't good enough here. See, the tile location actually doesn't matter. Let's see, what are you doing with find distance? I guess we need to look at that. So you're taking a row and a column, but you're not doing anything with it. You're not even using the row and the column. What you actually need is, yeah, and you're just penalizing it based on the height. That's not correct. You need the penalty for height is for a change in height. So if I'm at 2,000 meters and the person to my right is at 2,000 meters, that's no height penalty at all. So you need to do something like this, like change it to be my height and the new height or something like that, and is diagonal. Okay, so if it's diagonal, it's going to be 20 times the absolute value of height minus my height. And it doesn't matter which one you do first, or even which one's height. Which one is my height? It doesn't matter. All that matters is 1840 CW 1840, like that. So if it's the cardinal direction, the cost to move to that tile is 1840 plus 20 times the difference in elevation. Okay. This is the heart of the program right here. And so we're going to have to change all those calls to find distance because the row and the column don't matter in the slightest. What matters is the height of the current tile and the height of the new tile, and then it will do the subtraction and penalty for vertical change for us. Okay. 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 So now for all these find distance calls, we don't need the row, we don't need the column, we need our elevation, which is elev data dot at center dot x dot Oh, you're using X as the row. Okay. Okay. I guess it's fine. Dot at center dot y. So we're going to pass in the map data elevation for our current tile. We're going to pass in the map data elevation for the new tile, and it's, yeah, so in this case it is top, I guess. Okay. Yeah, usually X and Y. Ooh. Usually X means width, right? I don't know if that's going to matter at all, though. Row, column. So I guess if you're consistently using X for the row, I guess that's fine. Okay. All right, so tile top, all the directions work. Okay, that's fine. Okay, so but the problem is you were passing row and column to the find distance function when it doesn't, you weren't using it at all, right? What you need to know is the difference in elevation between the two. And wow, that's a lot of code. Do you want to see how I did it? Lot of vetting, all right, just to make sure. Checking to make sure that you don't navigate underwater. Okay, I've got my priority queue, I've got my process queue. I call reserve, which you don't have to do, but it's oftentimes, from a speed perspective, a good idea to tell a hash table or whatever how big it should be about. And so the hash table at most will hold width times height, number of tiles, right? So I say reserve that much memory. And then it doesn't have to do reallocations and stuff like that as it goes along. It's a little bit of a speed boost. It can give you like, I don't know, 25% speed improvement or something. And we're going to start. So this all looks very similar to yours, right, Vargas? You see that? Okay. So I'm going to pause the recording now so that people can't just copy this. And here, let me show you this part. So rather than copying and pasting that code 8 times, what I did was I just made a for loop that just goes -1 in the x direction, +1 in the x direction, -1 in the y direction, +1 in the y direction. And so the so I don't have to repeat myself, 8 times. So if it, and then if we're the current tile, it skips it. So then I do bounds checking to make sure that the new tile is within the bounds of the map. So I don't have to do that once, and then I've got the costs here. I grab the elevation data for my tile, the elevation data for the new tile. I don't travel over water. And then here's that's the elevation cost. Yours wasn't matching because you were going down is not preferred. Yeah, you want to stay even. Like if you have a truck, you don't want to send a truck off a cliff, you know what I mean? Or down a steep slope, or a railroad down a steep slope. You want flat. Flat's usually best. So that's that. So the move cost is that if we're straight, that if we're double, and then there's a penalty of 20 times the difference in elevation gain. And yeah, this is a cute little approach. There's an even cuter approach you can do where you use a range-based for loop. So you can do something like this. A vector of ints called move row. It's initialized to -1, 0, and 1. And move call, which is initialized to -1, 0, and 1. And then you can say for int I in move row, for int j in move call, And then if you see out I and j, this will print out all combinations of directions, right? So -1, -1, -1, 0, -1, 1. So all 9 directions technically, because it's going to give you 0, 0 also. And so this is a really kind of clever way of having code that goes in all 8 directions at once. So. Okay, so that's that, and then we make a new child. The child has the new x, the new y location, the current x, the current y is the parent, and then that's Dijkstra's right there. That's Dijkstra's. If you screw that up, you get minimal spanning tree. If you add in to that the Pythagorean distance to the end zone, the end tile, you get A star. That highlighted bit right there. That's it. Okay. So add a new child, and then if we're already in the processed queue, we skip it. Otherwise, we add it to the toProcess queue, and that's it. That's the whole assignment. The only other thing you have to do is backtrack. So once you hit the end zone, you have to write a for loop that will sit there, or a while loop that will go backwards along the map, going to the parent, going to the parent, going to the parent of that tile, going to the parent of that tile, going to the parent of that tile, until you hit the starting node. Yeah. So I'll give you guys till Thursday to finish this, and I'll give you a new homework assignment now. Yeah, you were laying down the path as you're going, but the problem was then when you were doing the elevations, your current spot is always going to be at -1 elevation, which is just going to break all of your, it's going to break all of your elevation computations. So you can set it to -1. No, you can't, because then it's going to render, the elevation of the entire map as -1. It'll destroy the entire map. The only spots you want to set to -1 are the ones that are on the shortest path to the end zone. Okay. So your next homework assignment is more bridges. Okay, so why don't on that note, why don't we take a break, come back at noon, and then we will start on your next nightmare office major assignment. Okay, so let's come back at noon, and if you have any questions about the Dijkstra's assignment, just put it up in the chat. Okay.